This is Mr. Liao, and this is section 6.2, probability models, and we're on the second part of the video. The first part of the video you can probably find, if I actually have time to make a link, on this screen. We are going to resume our discussion of probability rules with independent events. Suppose you toss a fair coin twice. Let's let event A mean that the first toss is heads. Let's let event B mean that the second toss is heads. We want to know the probability of both A and B happening. Well, we would expect the probability to be 0.5 times 0.5. The first 0.5 represents the probability that the first toss is heads. The second 0.5 represents the probability that the second toss is heads. Multiplying them together, we get a probability overall of 0.25. These two events are called independent events because the outcome of one event gives no information on the outcome of another. By definition, if two events are independent, they cannot be mutually exclusive. If you notice, you could have gotten heads on both coin tosses. That is, they are not mutually exclusive. They both could happen at the same time. So independent events are not mutually exclusive. Likewise, mutually exclusive events cannot possibly be independent because the two events cannot both occur. So if one event happens, we know that the other can't happen. So the probability of one event gives us information about the probability of another event. If I want to know the probability that I'm going to be in Milpitas on a Saturday compared to the probability that I'll be in San Jose, if I tell you that I'm in Milpitas, you know that I can't possibly be in San Jose. The fact that I'm in Milpitas gives you information to conclude that the probability of me being in San Jose is 0. So two events are mutually exclusive, cannot also be independent. Two events that are independent cannot be mutually exclusive. But events can be neither mutually exclusive nor independent. So they can be one or the other. They could be neither, but they can never be both. So examples of independent events: multiple coin flips, rolling dice more than once, drawing cards with a replacement. All these chance outcomes, basically you're starting at the beginning with each trial. Taking your blood pressure twice in succession. That doesn't really, you can't really do anything to change your blood pressure within a minute. You can hold your breath, you can relax. That doesn't change your blood pressure a whole lot. Two events that are not independent. Drawing cards without replacement. If you take out one card, don't put it back, that affects the probability of drawing any one of the remaining cards. If you take an IQ test twice in a row, you can use the information on the first test to score higher on the second test. So the two events are not independent. Taking the first test will probably tell me that you'll do better on a second test if you take it right away. This is Rule 5, the multiplication rule of independent events. Two events are independent if one event occurring does not give any information that the other occurs. So if two events are independent, the probability of A and B is equal to the probability of A times the probability of B. This is only true if two events are independent. This is not a general multiplication rule. We'll look at that in about a week. But this is only for multiplication rule for independent events. If two events are independent, this has to be true. If this is true, then the two events have to be independent. So it goes both directions. So let's go back to our playing cards. If you choose a random card from a normal deck, what's the probability of choosing a king or a jack? Well, there are 4 kings and there are 4 jacks in the deck. They do not overlap. So the probability of drawing one of them plus the probability of drawing the other is the sum of the probabilities that are individual. So 452 plus 452, there are 8 cards in the deck that are either a king or a jack, which comes out to 2 out of 13 or 0.154. What is the probability of drawing a single card that's both a king and a queen? Well, a card cannot be both a king and a queen at the same time. So the probability of both happening is 0. These are two mutually exclusive events. If you draw a king, you know that the card cannot possibly be a queen. If you draw a queen, you know that the card cannot possibly be a king. So the events are mutually exclusive because one person cannot draw both of the same card on one card. So let's look at part C. A card is chosen from a normal deck. What is the probability of choosing a king and a red card? Well, unlike the previous example, it is possible for a king to be also a red card. Which are the cards that are both king and red? That would be the king of hearts and the king of diamonds. So those represent 2 out of the 52 cards in a deck. So 2 out of 52 is 1 out of 26 or 0.038. Now, I didn't put this on your note sheet, but I wanted to know, are these two events independent? If they are independent, well, the probability of drawing a king that is red is equal to the probability of drawing a king at random times the probability of drawing a red card at random. How many kings are there? Well, there are 4 kings out of 52. How many red cards? 26 red cards out of 52. Multiply them together, you end up with 1 over 26, which happens to match the probability we got on the previous screen by just counting how many cards are both red and kings. So since the probabilities were the same, the 2 events are independent events. Last example, what is the probability of choosing from a single card a card that is both a face card and a heart? Well, this is what we're looking at. A face card are the kings, queens, and jacks, and the hearts are the 13 hearts. So let's figure out how many ways are there to get a face card that is also a heart. Well, there are 3 of those hearts in the deck. They're the king of hearts, the queen of hearts, and the jack of hearts. The probability of choosing any of those 3 is 3 out of 52, or 0.058. Now, are these 2 events independent? We'll find out. Let's take a look. If you multiply the probability of getting a face card times the probability of drawing a heart, that has to equal the probability that we just calculated. So the probability of getting a face card is 12 out of 52. There are 3 face cards in each suit, 4 suits for a total of 12 cards. 13 out of 52 represents the probability of getting a hearts. 13 out of 52 cards in the deck are hearts. Multiply them together and you get 3 out of 52, which happens to be the exact same probability in the previous calculation. So thus the drawing of a face card and drawing a heart are independent events. Alright, hopefully I'll be back by Wednesday. If not, I'll make another video or we'll have a review session. If you have any questions in the meantime, please post a message on the Facebook page or email me directly, because that's the best way for me to respond.